Hello there, this is Ms. Page, and this lesson is on finding an inverse function model from an original function, and it is part of our Unit 7 on radical equations. So we've looked at this concept before. When we're looking at an inverse function in context, we solve for the independent variable. We don't switch the variables. We just use our algebra skills to write a new function that isolates the independent variable. So, for example, given a function here that models the volume of a cube relative to its side edge here called S, the inverse function of that would actually solve for S. And that would give us S equals the cube root of V, where V is the volume. So it's just using the algebra to solve for the independent variable in the original function. We're also going to be looking again at identifying the domain and the range of our inverse models. So what we know about an inverse is a function and its inverse is that the domain and the range switch. So the domain of an inverse comes from the range of the original function, and the range of the inverse comes from the domain of the original function. So we have that switching situation. Sometimes our domains may have to be restricted, especially when we're working with square roots, and when we're working in context also, because we can't have like negative measurements in many situations. Negative inches doesn't make sense, and things like that. Negative time doesn't make sense. All right, and then this is just for reference. It's our undoing algebra, which again uses that reverse order of operations. Here it is actually outlined for you. We have talked about this and been using this for quite some time now. All right, so let's take a look at this example. So here it says the function f of a models how many feet of fencing a farmer needs to buy how much fencing he needs to buy to make a square holding pen with a 6-foot gap for a gate, where A is the area of the holding pen in square feet. So the function is our modeling how many feet of fencing a farmer needs to buy, which will make a square holding pen that has a gap of 6 feet for a gate. So remember, function refers to the y quantity. So that's saying f of a models that fencing amount. And then a is the area of the holding pen in square feet, which is our independent variable. And f is our dependent. The importance of that is towards domain and range of our inverse when we get there. So for our function, we know that a must be our domain quantity because it's the independent variable. So this is our domain, the area in square feet. And f, which is our dependent variable, our function value, that's our fencing in feet. So that is the range of the original function, and they will switch in the inverse. So in this first part, we are looking at writing the inverse function that will find the area of a square holding pen with a 6-foot gap for the gate, given the amount of fencing. So that wording there tells us that we want, since area is A, capital A, then what we are looking for is an A equals function. So we start with our given function, f of A equals 4 times the square root of A minus 6. Remember, do not change the case of the variables. Capital A stays capital, lowercase f stays lowercase. We've learned that in order to do this, what we need to do is simplify the function notation to just the variable that represents the dependent quantity, which would be f for fencing here. So we simplify. From here now, we use our undoing algebra to solve for a. So we undo our subtraction first, adding 6 to both sides. Then we undo our multiplication, dividing both sides by 4. And we'll just divide this entire quantity by 4. In these problems, it will be fine to leave this as a ratio. So now we have is the square root of a equals f plus 6 all divided by 4. Just switched my sides. And then we're going to square both sides to undo our square root, which is our exponent situation. And the square and square root undo each other, giving us a equals. I'm going to put that over here. There's no need to simplify this. So what we've got is f plus 6 all over 4, quantity squared. And then function notation for this inverse function. Now f is the independent variable, so it becomes a of f equals f plus 6 all divided by 4, quantity squared. And this is our inverse function model that will find area given the feet of fencing. All right, so now in part B, we are looking at describing the domain and range of our inverse function model and including restrictions on the variables. So that's why I can go back up to here, what I was talking about and identified earlier. So the domain of our inverse, so looking at the domain of the inverse, must be the same quantity as the range of the original function. So that makes the domain the feet of fencing, a farmer needs to buy. And the range of the inverse will have to have been the domain of the original function, which is the area of the holding pen in square feet. So it is area of the pen in square feet. All right, now let's take a look at our restrictions. So going back to our feet of fencing that a farmer needs to buy. So what we're looking at here is a situation in which we have to be able to actually create a holding pen that has a 6-foot gate, which actually means the minimum side length would have to be 6 feet. Like if the gate took up the entire length of one side. So if you had a square holding pen where one side was your gate, that is 6 feet. And that means that the other 3 sides would be fencing, all of 6 feet. And so actually the minimum number of feet of fencing for this problem actually has to be 18. So it's where your F value has to be greater than or equal to 18 in this case. For your range, which is your area then, what you're looking at, if this is the smallest holding pen that you can make, then the area is going to have a minimum value of 36 square feet. So here, our area, so where A, which is capital A, is going to be greater than or equal to then 36. All right, and then here we're looking at using a function model. So estimate the area of a square holding pen with that 6-foot gate if it has 128.5 feet of fencing, round to 3 decimal places in this case. So that means I would use my area function. So my area, A of F, would be equal, and just A or A of F. So I've got my F plus 6 divided by 4, quantity squared, and my F would be my 128.5. So this becomes 128.5 plus 6, all divided by 4, quantity squared. Here definitely a calculator would come in handy. And if you're going to put this into the calculator all at once, do make sure you put parentheses around the sum before you hit divide by 4. Otherwise, only the 6 is going to be divided by 4, not the sum. Or just subtotal this and then divide by 4 and then square that number. That would, of course, work too. So 2 3 decimal places, we are looking at 1,130.641. And so again, we need to know the units here, and area was defined as in square feet. And then we write our conclusion, as we always do. So the area of a square holding pen with a 6-foot gate and 128.5 feet of fencing is about 1,130.641 square feet. All right, so that completes all the parts for the first example. Let's take a look at this second example now. So here it says the function h equals models the shoulder height h in centimeters of a particular elephant at t years of age. So the function, that's our h, models the shoulder height in centimeters of a particular elephant. This is our function, of course, here. And the h is our shoulder height. And our t is defined as years of age of the elephant. Based on the structure of the function, t is embedded in the function rule. That makes it our independent variable, telling us the t values are the domain of this function. And h, which is isolated, is then the dependent variable, and its values would then be the range. So the shoulder height are the range values of this function. All right, so part A, we're going to write the inverse function that will actually find the age of the elephant in years, which means t equals. That's what we're looking for. So our function, h equals 62.1 times the cube root of t plus 76. We begin solving for t. So we would subtract the 76 on doing the addition first. Then we'd undo this multiplication, dividing both sides by the 62.1. Again, no need to do anything to try to simplify this. Writing it as a ratio will be fine in the context model. And then we have to undo our root, which is our exponent, remember, raising both sides in this case to the third power. And cube and cube root will undo each other, giving us t equals. And this would be h minus 76, all divided by 62.1, all raised to the third power. And this particular function model, which was just written as h equals, then I would say it would be reasonable to just write this one as t equals. You could, of course, also write t of h. That would also be appropriate. So either way would be fine here, I would say. All right. So now domain and range of the inverse function, which is our answer to part A. Domain and range of the inverse. So, again, what we know about an inverse is that compared to its function, the domain and range have switched. So when I'm looking at the domain of the inverse, it must be the same thing as the range of the function. So the range was the shoulder height in centimeters of a particular elephant. So shoulder height in centimeters of a particular elephant and the range of our inverse function would have to have been the domain quantity, which is the age of the elephant in years. So we'll say age of the elephant in years. All right, now let's talk about restrictions. So going back to our shoulder height in centimeters. This requires a little bit of mathematical analysis because we want to think, okay, well, shoulder height needs to be positive, greater than 0, which is true. However, in the context of our model, if we even use a shoulder height of 1, then this quantity would be negative, and t would then be the cube of a negative number, which would be a negative number, which doesn't make sense. And so what we have to realize here is that we actually have to be larger than, or actually greater than or equal to 76. If h is 76, this part becomes 0, which means we have 0 cubed, which makes t 0 years, which would be equivalent to the birth of this elephant. So basically it's saying, okay, at birth, the shoulder height of this elephant was actually 76 centimeters. And that would be our restriction. So where h would actually have to be greater than or equal to 76. That would then correspondingly make t, the age of the elephant, greater than or equal to 0 years, which makes sense in terms of the context. So where our t is greater than or equal to 0. All right, so now let's take a look at this application down here. So this one says to estimate the age in years and months of the elephant, specifically when its shoulder height is 193.4 centimeters. And again, round to 3 decimal places. All right, so we want age, that's our t, but t in our function is defined in years, so that means we'll have to do a conversion at the end into years and months. So we're looking at our t will be equal to our shoulder height. That's going to be our 193.4 minus 76, all divided by 62.1, and then raised to the 3rd power. So again, calculator comes in handy here. And again, if you're going to put this all into the calculator at once, do make sure you put your difference in parentheses before you hit divide by the 62.1, and then raise that quantity to your 3rd power. And then doing that calculation and rounding to 3 decimal places, we get about 6.757, and this would be years. It would actually be best if we just used this entire thing like so. So now, instead of rounding, so I'm just carrying it out, but I'm not actually going to round it. So this, remember, would be our whole quantity of years for years and months. And then we need to convert our decimal portion of years into months by multiplying that part times, we want to get rid of years, and we want to turn it into months. We want our months in our numerator. So 12 months in 1 year. So we're going to have to take this times 12. So remember, what you want to do is simply subtract off the 6 in your calculator, so you're left with all of this decimal, and then take that times 12. And now I would say round to 3 decimal places at this point. So this would become an approximate quantity still, and you would get 9.079, and that would be your months. Like so. And then we can write our conclusion. So age of the elephant is about 6 years, 9.079 months. When its shoulder height is 193.4 centimeters, like so. All right, so those are the basics, and that you are now have both the examples that were planned, and you may begin your assignment. Have a good day.